Here is something that'll ruin your day, and I mean that as a compliment. Most people, when they think about going to another star, they think bigger rocket, more fuel, maybe 100 years. Fine, wrong, embarrassingly wrong. Not a little wrong, catastrophically. Universe laughing at you? Wrong. I sat down and actually did the numbers the way a physicist does, not the way a dreamer does. And what came out the other end was so brutal, so unforgiving, that it stops most people cold. 1,000 years. That is not a typo. That is physics. And today I'm going to show you exactly why, step by step, so that the next time someone tells you we're almost ready to reach Alpha Centauri, you can smile and say, sit down, let me explain something. Me explain. You have never truly felt how fast you are moving right now. Sitting still, watching this, you are hurtling through space at roughly 30 kilometers per sec. That is Earth's orbital speed around the sun. 30 kilometers every second. You feel none of it. No wind, no force, no sensation whatsoever. The universe has made you completely numb to a speed that would vaporize any aircraft ever built. And here is the uncomfortable part. 30 kilometers per s is nothing. It is embarrassingly, almost insultingly slow compared to what interstellar travel actually demands. If you wanted to cross the distance between us and the nearest star at that same speed, the trip would take roughly 43,000 years. So before we talk about ships, before we talk about fuel, before we talk about any of it, we need to agree on one thing. The scale of this problem is not what you think it is. And once you see it clearly, you cannot unsee it. The nearest star to our sun is called Proxima Centauri. It sits at a distance of 4.24 light years from Earth. That phrase, light years, gets used so casually it has lost all meaning. So let's restore it. A light year is the distance light travels in 1 year. Light moves at 300,000 kilometers. In 1 second, it circles the Earth 712 times. In 8 minutes, it reaches the sun. In 1 year, it travels about 9.46 trillion kilometers. Multiply that by 4.24. That is the distance to Proxima Centauri. Roughly 40 trillion kilometers of cold, empty, silent space. And the word that matters most in that sentence is empty. No fuel depot, no rescue, no second chance, just darkness, distance, and the quiet indifference of physics. Here is something worth pausing on. That emptiness is not just a logistical problem. It is a psychological one. Every mission humans have ever sent into space has had one invisible safety net. The possibility of return. Apollo astronauts were 3 days from Earth. The International Space Station is close enough that an emergency evacuation can have a crew back on the ground within hours. Even the most ambitious Mars proposals assume a return window, a rescue scenario, some thread connecting the travelers to home. An interstellar crew has none of that. The moment that ship reaches a certain distance, the thread does not just stretch. It breaks completely, permanently, no resupply, no evacuation, no communication that isn't years delayed in each direction. You are a one-way passenger on a vessel that must be its own entire civilization. That psychological reality changes everything about how you design the mission, how you select the crew, how you structure the society on board. And we have barely begun to think seriously about it. The farthest object humanity has ever launched is Voyager 1. It left Earth in 1977. It has been flying for nearly 50 years without stopping. Right now, after half a century of uninterrupted travel, it is about 23 billion kilometers from Earth. That sounds enormous. But set it against 40 trillion kilometers, and it becomes something almost painful to look at. Voyager 1 has covered roughly 0.06% of the distance to Proxima Centauri in 50 years. At its current speed, it would take approximately 73,000 years to reach our nearest stellar neighbor. Agriculture is about 12,000 years old. Writing is about 5,000 years old. Voyager would need 6 times the entire span of recorded human history just to reach the closest star. That is the baseline. That is where we start. To reach Proxima Centauri in any time frame worth planning around, you need to travel at a meaningful fraction of the speed of light. At 1% of the speed of light, the journey takes 424 years. At 10%, about 42 years. 10% starts to sound almost workable. So the question becomes, what does it actually take to push a spacecraft to 10% the speed of light? The answer is energy. Energy on a scale with no comparison in human experience. The kinetic energy of any moving object increases with the square of its velocity. Double your speed. You need 4 times the energy. Go 10 times faster, you need 100 times the energy. Every additional increment of speed costs exponentially more than the last. And you cannot arrive at another star at full speed. You would blow straight through the system in hours. You have to decelerate. Deceleration costs exactly as much as acceleration. You pay the full bill twice. The universe does not offer refunds. Chemical rockets, the kind that took humans to the moon, are completely categorically inadequate for this. Not underpowered, inadequate. The best chemical propulsion gets you to perhaps 0.001% the speed of light. At that speed, Proxima Centauri takes over 400,000 years. So chemistry is not the answer. Nuclear fission is better. A fission drive could push a spacecraft to around 0.1% the speed of light, getting you there in roughly 4,200 years. Still impossible for any crewed mission, but the direction is right. Nuclear fusion is where real hope lives. Fusion powers the sun. It releases vastly more energy per kilogram than fission. A fusion drive could theoretically push a ship to between 1 and 10% the speed of light, putting Proxima Centauri between 40 and 400 years away. That starts to feel like something a civilization could attempt, except we have been trying to achieve controlled fusion on Earth for 70 years and still haven't done it reliably. Scientists joke bitterly that fusion power is always 30 years away. It has been 30 years away since the 1950s. That is not a reason to give up. It is a reason to be honest about where we are. The physics of fusion is sound. The engineering is extraordinarily hard. The materials required to contain a fusion reaction. Temperatures hotter than the core of the sun, held stable long enough to extract useful energy, push the limits of everything we know how to build. Progress is real. Timelines are uncertain. And even if we solved fusion tomorrow, we would immediately hit the second wall, fuel mass. There is an equation called the Tsiolkovsky rocket equation derived in the late 1800s, and it has haunted every rocket engineer since. It tells you something brutal. To go faster, you need exponentially more fuel relative to your payload. For a fusion ship trying to reach a few percent of the speed of light, the fuel-to-payload ratio becomes catastrophic. Some estimates suggest you would need hundreds or thousands of times more fuel mass than payload. If your spacecraft weighs 1,000 tons, you might need millions of tons of fuel. And that fuel must be accelerated too, which requires more fuel, which adds more mass, which requires more fuel. The spiral is relentless. Every solution creates a larger version of the same problem. There's a concept in rocket science called the mass fraction. It describes what percentage of a rocket's total weight at launch is fuel versus everything else. For the Saturn V, the most powerful rocket ever built, the one that sent humans to the moon, the mass fraction was about 85%. That means 85% of the entire rocket was fuel, only 15% was structure, engines, crew, equipment. For an interstellar fusion ship, the mass fraction approaches 99% or beyond. The fuel does not just dominate the ship, the fuel essentially is the ship. Everything else, the people, the life support, the destination systems, the 1,000 years of supplies is a rounding error sitting on top of an ocean of propellant. And that ocean has to be manufactured, stored, and transported from somewhere, which raises a question nobody in popular discussions ever asks directly. Where does the fuel come from? Who builds it? How long does that take? The ship does not just require a new kind of engine. It requires an entirely new kind of industrial civilization, capable of producing fuel in quantities that have no precedent in human history. The most serious modern proposal for reaching another star in a human-relevant time frame is Breakthrough Starshot. It solves the mass problem by making the spacecraft nearly massless. A sail a few meters across carrying a chip the size of your fingernail. Lasers fired from Earth push the sail to 20% the speed of light in minutes. It reaches Proxima Centauri in about 20 years. Real physicists are working on this. It is not science fiction. But notice what it is not. It is a chip, not a person, not a crew, not a future. It can take photographs and send data back, data that takes 4.24 years to arrive at the speed of light. The best possible outcome is a set of measurements from the nearest star arriving decades from now. That is genuinely extraordinary, and it is also the absolute ceiling of our most optimistic current thinking. Everything beyond that, any conversation about sending human beings leads straight back to the 1,000-year problem, because human beings are not chips. And that difference changes everything. People need air, not approximately air. Continuous, breathable, carefully managed air recycled without failure for the entire journey. People need water. People need food grown and produced continuously in an enclosed environment for generations. People need medicine, not a pharmacy that runs out in 50 years, but real medical capability applied for 1,000 years. People need gravity or their bodies begin to fail. Without it, bones lose density, muscles weaken, eyes change shape. The cardiovascular system adapts in ways that make it poorly suited for life on a planet. These are documented effects observed in astronauts after months on the International Space Station. Multiply months by 1,000 years. There is another dimension to the biology problem that rarely gets discussed: evolution. Human beings evolve for one specific environment, one specific gravity, one specific radiation level, one specific daylight cycle, one specific atmospheric composition. We are precisely tuned by billions of years of natural selection for the conditions on this one planet. Put us anywhere else and we begin to drift, not immediately, not dramatically, but over generations in a closed population. On a ship with artificial gravity, artificial light, recycled atmosphere, and constant low-level radiation exposure, the human body will change. The immune system will respond to a different set of threats and lose calibration to others. The microbiome, the trillions of bacteria that live in and on us and that are essential to our health, will shift in ways we cannot predict because it has never existed in this environment before. Children born on the ship will not be identical to children born on Earth. By the 10th generation, the differences may be subtle. By the 50th, they may be significant. By the time anyone arrives at Proxima Centauri, the people stepping off that ship may be meaningfully different biologically from the people who stepped on. We have no data on this. We have no model for it. We have only the certainty that living systems change when their environment changes. And 1,000 years is a very long time. A crewed interstellar ship is not a vehicle. It is a world, a closed, self-sustaining world that must function without external support for longer than the United States has existed, longer than the printing press, longer than the Renaissance, the Industrial Revolution, and the digital age combined. Every system must work, not mostly, continuously, regeneratively, without permanent failure across a millennium. We have never built anything that lasts 1,000 years without outside maintenance. Our oldest buildings are ruins. Our oldest machines are museum pieces. And then there is radiation in deep space. Earth's magnetic field and atmosphere are gone. Cosmic rays, high-energy particles produced by supernovae across the galaxy, pass through metal, through water, through the human body, damaging DNA as they go. Over years and decades, the damage accumulates. Cancer risk rises significantly. Materials degrade. Shielding helps. But shielding is heavy, and weight is the enemy of everything in interstellar travel. More shielding means more fuel. More fuel means a larger ship. A larger ship needs more shielding. Every solution pulls against every other. Now, set the physics aside. Think about the human part, because the human part may be the hardest part of all. The first generation boards the ship on Earth. They chose this. They remember rain. They remember open sky. They will die on the ship. Their children are born on the ship. Those children grow up in metal corridors under artificial light, breathing recycled air, surrounded by the same few hundred people for their entire lives. Earth is something that exists in stories and recordings and the fading memories of elderly people around them. By the 10th generation, the founders are gone. By the 20th, they are history. By the 50th, they are mythology. And the mission, the goal of reaching a star that no one alive has ever seen, set by people so long ago, they might as well be ancient ancestors, must somehow remain the organizing principle of an entire society. How do you build a culture around a purpose no one chose? How do you raise children to care about a destination their great-great-grandchildren might reach? We have never answered them. We have never even tested it. The longest isolated human communities we have studied all had one thing the ship does not. They knew the rest of the world existed and could be reached. The crew of an interstellar ship is more alone than any human beings in history. Consider what governance looks like on a ship like this. Who makes decisions? Who holds authority? What happens when a faction of the crew, perhaps by the 30th generation, decides the mission is not their responsibility? They did not sign up for this. Their great-great-grandparents did. Can they turn back? Number, there is no back to turn to. Earth is so far behind them that the concept of return is meaningless. They are committed not by choice, but by birth. That is a situation with no historical precedent. Every civilization that has ever faced a crisis of legitimacy, every revolution, every collapse, every moment when the governed decided the governors had no right to rule, had somewhere else to go, a physical frontier, a new land, a border that could be crossed. The crew of an interstellar ship has none of that. The frontier is in front of them 1,000 years away. Behind them is nothing. Around them is nothing. The ship is everything. And whoever controls the ship controls the only reality that exists for every person alive. That is an extraordinary amount of power concentrated in an extraordinary amount of isolation. What it does to human society over a millennium is genuinely unknowable. Some proposals try to skip the generational problem entirely, freeze the crew. They sleep through the journey and wake at the destination. Biologically unchanged, no cultural erosion, no psychological unraveling across centuries, except we do not know how to do it. Freezing a human brain with its 86 billion neurons and 100 trillion synaptic connections and restoring it to full function without damage is not something we can demonstrate. It may be possible. Researchers are working on it seriously. But a mission that depends on technology we cannot yet demonstrate is a mission that cannot yet be planned. Step back further. Look at this as a civilizational problem rather than an engineering one. Because the right level of analysis here is not the rocket. It is the civilization that builds the rocket. We are currently at roughly 0.73 on the card scale, a framework that ranks civilizations by energy use. A Type 1 civilization uses all the energy available on its home planet. We are not there yet. The energy required for true interstellar travel is Type 2 territory, harnessing not a planet's energy, but a star's. We are not close to that, but the direction is clear if we choose to move in it. And here is the part that matters most. The reason you do the math is not to feel defeated. The reason you do the math is to know where you are. A doctor who refuses to look at an X-ray because the results might be bad is not a good doctor. A physicist who avoids the calculation because the answer might be discouraging is not doing physics. The honest numbers, brutal, unsparing, indifferent to our feelings, are the beginning of real work. Once you know chemical rockets are inadequate, you stop wasting energy on them. Once you know fusion is the threshold, you focus there. Once you know the fuel mass problem is the central obstacle, you think about every possible way to reframe it. The numbers are not a wall, they are a map. They show you exactly where the work is. There are people doing that work right now, designing closed-loop life support systems that recycle air and water with near-perfect efficiency, building radiation-hardened materials for deep space, studying the psychology of isolated communities to understand what humans need when cut off from the world, designing propulsion concepts, nuclear pulse drives, laser systems, antimatter engines that exist as math on paper, but math that violates no known law of physics, thinking seriously about how a society governs itself across leadership transitions, spanning not years but centuries. These are real questions. Real progress is being made on all of them. The timeline for interstellar travel is not measured in decades. It is probably not 1 century. It spans multiple centuries at minimum. The technology must mature. The energy infrastructure must transform. The scientific understanding of biology, psychology, and closed ecological systems must deepen enormously. And somewhere in that long arc, the 1,000-year problem may begin to shrink. Not because the stars get closer, they don't, but because we become faster, smarter, more capable, and more patient. Because a civilization doing the math becomes something different from what we are today. That is the honest picture, not hopeless. Honest, every impossible journey in human history looked impossible, until it didn't. The first people to cross open ocean in small boats had no instruments, no charts, no knowledge of what lay beyond the horizon. They went anyway. The first engineers to suggest a machine could fly were laughed at until the morning they weren't. None of those breakthroughs happened because people ignored the obstacles. They happened because people understood the obstacles precisely and worked on them with everything they had. The ship does not exist. The fuel is not solved. The crew has not been born. The destination is a faint point of light 40 trillion kilometers away. Ancient photons arriving from a place no human being has ever been. And somehow looking at all of it clearly, the distance, the physics, the 1,000 years, the unsolved problems stacked on top of each other, it still does not feel like if. It feels like when the answer to when depends entirely on what we decide to become. The star will burn for billions of years whether we go or not. It does not know we exist, but we will know whether we tried. We will know whether we looked at the honest numbers and worked on the hardest parts without flinching. That is the only choice a civilization actually gets to make. Not the distance, not the physics, just whether it looks up, does the calculation, and begin.